So this is a technical lecture on the Einstein equations. Today I'll try to give an intuitive geometric meaning to them, and we'll try to correct the mistake uh, made in the derivation in the previous lecture. Okay, so previous time we start from the observation that in the presence of the massive body, the space-time is getting curved. And we notice that what curvature actually uh, is the convergence or deviation between geodesics, right? So if you had two geodesic parallel to each other here, very far away in flat space, next to the massive body, this starts to converge like this. And this convergence is what's measured by the Riemann tensor. But today I'll try to write it down more precisely. If you have a family of geodesics parameterized by parameter s, this say vector x mu, the family is parameterized by parameter s, each geodesic is parameterized by parameter tau by its proper time. I've introduced two vectors, t mu, which is a tangent vector, and a vector measuring the distance between geodesics. There will be an equation controlling the rate of this deviation change, actually the acceleration of this deviation change with respect to proper time as soon as we move along these curves, involving the Riemann tensor. Second derivative with respect to proper time is equal to the Riemann tensor okay, so that's the equation. Notice, by the way, that the Riemann tensor has symmetry in the indices nu rho and mu sigma. So if we define the Riemann tensor on the quadratic form on a vector t, pair vectors t and pair vectors s, sorry, a pair vectors t and s, it's enough to determine it completely. Because any bilinear form symmetric form, if it's symmetric, is actually uniquely determined by the corresponding quadratic form. So we'll use this kind of isomorphism all the time. Now, that's step one. We actually also noticed that at least in a simple model for our universe, for the curvature, we don't expect the volume spanned by geodesics to change along its flow outside of gravitating body, but only the shape. Each volume uh, will be getting stretched in one direction, but contracted in the opposite direction. So that's led us to conjecture that outside of the gravitational bodies, what's called the Ricci tensor should be equal to 0. Because the Ricci tensor is precisely what controls the change of volume along the geodesic flow. Yeah. So if you have like geodesic, and you have an infinitesimal volume here, and the Ricci tensors control how this volume gets changed. Concretely, there is an equation like this. This is our infinitesimal volume minus the same change in flat space. You could think about it physically like this. If you have a small cloud of particles of dust, some volume here, and they all start to move along neighboring geodesics, how will this volume change? Volume of the cloud. Will they start drift further apart or closer to each other or what? So Riemann tensor would have remembered information about each separate particle, right? And control was it deviate, was it getting closer to this trajectory. But Ricci forgets it and only remembers about the total volume. And that's why Ricci tensor appears in the Einstein equations. However, there is a certain subtlety, which I briefly mentioned previous time, is that Einstein equation is not just matter causing Ricci curvature. It has certain correction. Correction has something to do with what's called Ricci scalar. The Ricci scalar is a contraction of the Ricci curvature. Just like the Ricci tensor itself is a contraction of the Riemann tensor, right? a certain average of curvatures, and has a separate intuitive meaning. Actually, what it does, it controls the volume of a ball of size epsilon in our space and compares us to the same ball in flat space, flat geometry. Side-down manifold. As an example, I could show you how this calculation works on a, say, two-dimensional sphere. We have a sphere with coordinates theta, phi, and we want to calculate this area, right? The volume on a sphere is the area. So this distance is equal to r theta, which is our epsilon. And we know that the volume form on a sphere is just what? R square sin theta d phi d theta. So in order to calculate the area, we are writing down this integral. Which gives us and we could expand it a little bit like this. 1 minus 1 plus theta square over 2 minus theta to the power 4 over 24 plus dot dot dot. This will give us 2 pi r square theta square over 2 minus theta 4 over 24 plus dot dot dot. And we see that this term gives us precisely the area in a flat space, PR theta square, right? Standard formula for the area of the circle, right? And here we have some correction. Right? And this should be equal to, according to the formula, 1 minus r theta squared. Dimension is equal to 2. So it's 6 times 4. Yes. Plus dot dot dot. So we see from here that S, scalar curvature of a sphere, is equal to 2r squared, where r is the radius of a sphere. So indeed we see that because of that, this ball is getting slightly smaller than what it would have been in a flat space. Now, why I'm talking about all of it? So the problem which Einstein faced when running his equation is that when he wrote it like this, uh, somebody noticed that the right-hand side uh, is divergence free. Basically, energy momentum tensor satisfies continuity equations, right? Energy could not be created out of nowhere. It could just only flow. But the Ricci tensor does not satisfy it. And in some sense, there is a simple geometric meaning for it. Let's say you have, you start with some point here, consider some infinitesimal volume, and you see how it would grow along different geodesics. And if it grows in any direction you go, it's kind of natural to expect that the tensor which controls the change of volume along the geodesics flows has some sort of source here, just like with the vector field. That this curvature flows outwards here. And it turned out that this divergence uh, is proportional to coefficient 1/2 to the gradient of the scalar curvature, which probably makes sense, right? Because the scalar curvature is precisely the average of all those changes of all direction. Even if it's positive, it could if it's non-zero, yeah, it could act as a source for volume change along each geodesics, right? Because the scalar curvature precisely tell us, yeah, the gradient of it tells us how the size of a unit ball changes from here to here, right? Small here, it's big here. We would expect um, uh, the Ricci tensor to have a source proportional to the gradient of this change. Yeah, that's maybe not very intuitive. And this follows from the Bianchi identity. Rigorously, you could derive it. But I don't know how to make it more explicit, unfortunately, or more intuitive. But from here we see that if you subtract this 1/2, the symmetric tensor, wait, and call it uh, by definition the Einstein tensor, then it will be covariantly constant because symmetric is covariantly constant as well. So now we see that this curvature, this special trace reversed curvature, it actually behave like, like liquid or like energy. So if it grows in this direction, it have to decrease in some other directions. So it actually behaves like a flow, right? It flows from here to here in this picture. Doesn't have a source anymore. And that's why we could equate it to the energy, because the energy behaves in the same way. So Einstein equations just make them equal up to a certain coefficient, and this coefficient determines precisely the strength of the gravitational interaction. Yeah, but the question remains, what is the intuitive geometric meaning of this tensor? What does it mean? What this question means intuitively? And there is a explanation actually. So imagine you would like to have start with your Riemann tensor, but instead of calculating the total scalar curvature of the whole space, you would be interested in calculating the scalar curvature of the hypersurface. Mm, orthogonal to some unit vector. T mu. Then instead of contracting the Riemann tensor with just the metric G mu, you would contract it with a projection operator. Right? So you would write something like this. That would be, by definition, the scalar curvature of this three-dimensional slice orthogonal to T. At the same time, if you make the calculation, what you'll get is what we could do it right now. You'll get the scalar curvature minus 2 Ricci curvatures mu nu T mu T nu. Oh, so that's precisely minus 2 G mu nu T mu E nu. Therefore, G mu after this constant minus 1/2 precisely plays the role of a tensor which has information about scalar curvatures of any three-dimensional slice of our manifold orthogonal to vector T mu. Again, G mu is symmetric, so the information about it is uniquely encoded in the corresponding quadratic form. And that's what we're doing here. And same for the energy momentum tensor. So the right way to think about Einstein equations is actually contracted with some symmetric, contracted with some unit vector T mu. And if this unit vector is proportional to, is equal to, say, velocity, some observer moving with for vector speed u, then what this thing is just the energy density absorbed by the person moving with velocity u mu. And g mu nu, u mu nu is just the curvature of some hypersurface orthogonal to his motion. For example, if you just choose u mu to be some sort of vector like this, 1, 0, 0, 0, we literally will get that the curvature of a three-dimensional slice x, y, z, scalar curvature, is equal to use different notation, is equal to the usual energy density, which means the energy density creates curvature of space. You could say all other equations are just the way to make this equation generally covariant, that the meaning is encoded in this one, and all others obtained by general coordinate transformation from this one. So that's the geometric meaning of the Einstein equations. It's just the dynamics of the codimension one surfaces governed by the rule that at every moment the scalar curvature of this hypersurface is proportional to the energy density as perceived by the observer moving orthogonal to this hypersurface. So that's the end of today's discussion. Hope you enjoyed, and well, see you next time.